Today I'm going to present our most recent work on the chemical composition of Titan. But before that, let me give just a brief introduction to the ocean worlds, just for context. So we move to the outer solar system and the major icy moons of Jupiter and Saturn that are believed to be ocean worlds, meaning they have a water reservoir under their crusts. The best examples are Jupiter's Ganymede and Europa that contain 6 and 2.5 times more water than Earth, and Saturn's Titan that contains 11 times more water in analogy to its mass than Earth, our own planet. Titan, Saturn's largest moon and most Earth-like object in our solar system, is believed to have a subsurface ocean, either in direct contact with its ice shell or, in a sense, sandwiched between two icy layers, as shown here in the model. So Titan has been observed for 13 years by the Cassini-Huygens mission, which ended in 2017. Cassini completely changed our view of this exciting world and turned it from an orange ball, as you can see here on the left, to this detailed view on the right, taken in situ by ESA's Huygens probe, making it the first and so far only human-made object that landed in a body of our outer solar system. We know that Titan has a very dense, thick, and hazy atmosphere rich in nitrogen and methane that in a way shields the surface. A surface that consists of terrestrial-like features such as hydrocarbon lakes, liquid ones, of course, mountains, rivers, dunes, and possibly cryovolcanoes. Now, a couple of years ago at JPL, using Cassini and Huygens data from the entire Cassini mission, we created the first geomorphological map of Titan that I show here on the slide. And what this map told us is that Titan is governed by the undifferentiated plains that you see here with green color, followed by the dunes in magenta here in the equator, and the mountains in yellow, in addition to some small labyrinths and lakes at the poles, and also only a very small amount of craters. Even though many discoveries were made by Cassini, a large number of unanswered questions still exist. These include the so-called cold cases that Cassini was not able to resolve, and new questions that the Cassini findings, in a sense, created. One major unresolved mystery for Titan right now is the nature of its surface composition, how the surface evolves with time, and what are the relative geological processes involved. To answer these questions, actually, our team uses spectral imaging observation from Cassini's visual and spectral mapping spectrometer, or VIMS, that include both the atmospheric and surface information. As I mentioned earlier, the thick and hazy Titan atmosphere presents a barrier to the spectral exploration of the surface due to the methane absorption and scattering of atmospheric components in the VIMS data. And examples of VIMS data you can see here on the slide. So in order to extract meaningful surface information from VIMS, we're using the methane windows where the methane absorption is less than in other wavelengths. And you can see the centers of these windows in these peaks here in the plot. Still, though, even in these windows, we need a very good understanding of the methane and haze contributions to the opacity in order to extract accurate results. For that, our team at the Observatory of Paris developed a radiative transfer model built in Titan's conditions. The code gives us, on one hand, the Haze effect on the data. So an estimation of the contribution of the atmosphere in the VIMS data. And on the other hand, the absolute surface albedo, which is what we're asking for from the code to produce. Now, this code is a plain parallel radiative transfer code based on an SH DOM solver. The code includes several Huygens inputs, such as the temperature profile from Haze, the methane mixing ratio from GCMS, all these are Huygens instruments, the Haze parameters that we adjust from DISR, several atmospheric gases that you see here, and absorption coefficients that are produced in the right Titan conditions and for the first time in the full VIMS range. Descriptions of the code can be found in this paper, in these papers here, in these publications, lower in the slide. But briefly, when we take all these inputs into account, the code fits the simulation, as you can see here in orange color, with the VIMS data that you see here in black. And when the best fit is obtained, it provides an estimation of the Haze contribution to the data with respect to the measurements provided by the Huygens descent imager and spectral radiometer, or DISR, when Huygens descended through the atmosphere and landed on the surface in 2005 and took these measurements. The final product of the code is the extraction of the pure surface albedo in both full resolution, as you can see here in the 5 methane windows, and in weighted averages, as you can see here with the symbols. Okay. On another partition of the code, we include candidate materials for the surface of Titan, including laboratory thawing materials that, we include candidate materials for the surface of Titan, meaning materials that are expected to be present on the surface. And these are laboratory thawing materials that we expect Titan to have them in the atmosphere, and ices like water, methane, ammonia, carbon dioxide, in addition to cyanoacetylene, propane, ethane, ethylene, and even acetylene. And of course, as you can see here in the lower plots, we add bitumens, which are materials that we don't expect to find on Titan, but we use them as an agent to lower the albedo, because as we know, Titan is very dark. The lab work and spectra are produced by our collaborators in the University of Grenoble, which for the purpose of our project produce results convoluted to VIMS spectral resolution. So what this code does is fit it in the best way possible the extracted albedos from the regions of Titan with possible component mixtures. So using this unique tool, we have worked on several projects unveiling step-by-step Titan's complex surface composition. At first, as you can see here and there, we estimated the Haze contribution to the data from a large number of different areas on Titan and extracted their pure surface albedo. To our surprise, we found unexpected albedo differences and similarities. For example, regions with completely different morphologies, like the undifferentiated plains that you see here, and the adjacent labyrinth terrains there, which are heavily dissected areas, seem to have very similar albedo and hence consist of very similar materials. On the other hand, areas that look like, they don't look alike at all are built of, areas that do look alike, they seem to build of very different constituent mixtures. That dynamical range in albedos made us look at the possible temporal variations of Titan's region when we had good enough data for such an analysis, meaning overlappings of VIMS data. We looked closely at the candidate cryovolcanic areas, which are the most likely to be connected with the interior and present strong astrobiological interest, but also to a number of other areas that theoretically have an atmospheric origin.
5 more minutes.
Sorry?
5 more minutes.
Okay, good. So indeed, after analyzing 7 different units and more than 25 areas, we found 2 specific areas changing with time. We show one of the results here. Both these areas are cryovolcanic candidates, meaning that their morphology is compatible with volcanic units, and their names are Sotropatera and Tui Regio. In addition, recently we looked at the impact craters of Titan, which, like Earth, are not many due to the presence of the dense atmosphere and the constant resurfacing of the surface. And one of these craters is Selk. You see an example of a VIMS data cube here, including Selk, which is the landing site of the mission Dragonfly, which is the future mission to Titan. And here you can see the distribution of regions on Titan's map and the different geomorphological types that we used in our analysis, from definitions that we did based on radar data, and you can find very good descriptions of the various geomorphological units in these papers up here. And here you can see the first set of results and the constraints of the chemical composition of some Titan areas, which showed that Titan has a significant latitudinal dependence in its surface composition, with organic materials accumulated in the equator, as you can see here in magenta and orange color, and water rise in the mid-latitudes, as you can see here in light blue, and it's always over 30 degrees in latitude. Now, our current project at Caltech and JPL is to expand this analysis to a global one and add more constituents in the mixtures and create the first global compositional map for Titan. Here you can see the extension of the previous work where we added more areas. So what we want to do is to complete the map and make all the necessary connections with the interior and the geomorphology, which we take from another instrument of Cassini, the radar. This project has a lot of room for development as we plan to add the secondary constituents present in the mixture of the surface and so on and so forth. So in terms of landscape evolution scenario, our analysis has showed that active fluvial erosion is in a sense cleaning the surface in the mid latitudes up here and down there of what we call atmospheric deposits of organic materials, while absence of ice in the equator, with the exception of the Synlab crater, which is the youngest crater on Titan, suggests that that kind of cleaning that I mentioned before does not operate in the equator, but rather there is complete resurfacing occurring due to aeolian processes, at least at the very top layers of the surface. So it appears that active processes are working to shape the surface of Titan, and it remains in a dynamic world in the present day. This is a hypothesis that will be tested by the Dragonfly mission, which aims to investigate the crater Selk during its prime mission and identify the products of interaction between water, which was liquid at the time of impact, and organics. Now, why do we focus on the geology of these worlds? The answer is simple, and of course it's life. The reason why we concentrate on the geology, other of course than understanding the origins of our solar system, is also because by studying the geology, we're getting information on the requirements for habitability. And these are, as you can see here, liquid water, energy sources to sustain metabolism, and nutrients. And here on the right, you can see a sketch we created for a project we are running at JPL as part of a NASA Astrobiology Award, which focuses on tracing biosignatures on Titan from the top layer of the atmosphere down to the bottom of the underground ocean. So for instance, by identifying the surface composition of the ocean worlds, we get answers on the presence of liquid water and nutrients, and by detecting cryovolcanism or any other type of internal activity, we evaluate the energy sources sufficient to sustain metabolism. Now, earlier today, Athena Kostenis gave a great talk discussing all the current updates with regards to the ocean worlds and the future missions to these worlds, and mentioned that all big agencies focus on these targets. And indeed, one of the main themes of both NASA and ESA is the investigation for life and habitability in the solar system. And there's a great focus on the icy ocean worlds due to the subsurface oceans, and as I mentioned before, the fulfillment of the classical criteria for habitability. In the past 2 years, we have advocated strongly on that with a plethora of white papers in the recent decadal survey for NASA, and also ESA's Voyage 2050. And actually, and I encourage you to read some of these white papers. And actually, recently, the Voyage 2050 report came out stating that ESA's focus for large class science missions for the timeframe 2035 to 2050 will be the moons of the giant solar system planets. And this is also the case for NASA as defined by the NASA roadmap to ocean worlds. So it's obvious that the ocean worlds are places of great importance. And of course, we're all looking forward to the next mission to the ocean worlds, which is ESA's JUICE mission, the Jupiter Icy Moons Explorer. The JUICE spacecraft is currently being tested at ESA's facilities and is set for launch in 2022. Now, JUICE will spend at least 3 years investigating the Jovian moons Ganymede, Callisto, and Europa, while NASA's Europa Clipper mission will investigate Europa at around the same time as JUICE, with a planned mission launch in 2024. So with JUICE, we're all very excited to have the first ever mission, and specifically a European one, to orbit a moon other than Earth's moon. So I'll leave it to here, and since I'm in Hawaii, I'm saying goodbye with the Titan Tropical Resort and Hawaiian themed postcard, and I'll take your questions.
Thank you very much, Anezina, and also thank you very much for the nice talk, and also for staying so early in your morning to give you this talk. So please, time for questions, comments from the audience. So just speak up. Everybody's unmuted. So questions, comments? I got one question of technical manner. The data you're using, do you, in order to calibrate them, do you do that in ground also? Do you do it on the fly? How do you calibrate?
No, it happens at JPL. Mm-hmm. So yeah, the VIMS in a way calibration station is at JPL, and you know we work together with the people that calibrate the data, so we have a direct access. So when the data are calibrated, it's offered to the team members.